Okay, well, we've been talking about endo and exothermic and throwing around this term enthalpy, which we've referred to as the heat of reaction. Okay, so we've talked about how, and we've quoted a number of values for enthalpy, but we haven't really talked about how we can find these out. We did talk about how it is a state function and it's independent of path, and how we can only measure its effect on our system and surroundings. Well, what are the point? The effect of the system on the surroundings. We can't measure enthalpy directly. So what we're going to look at today is how we start to measure the heat of reaction, or how much heat is being put out from a given reaction, so we can start turning that into an enthalpy value. One of the key things that we need to understand here is when we talk about water. Okay, so in order for water to increase its temperature by a small amount, we actually need a large amount of energy. One of the least eco-friendly things you can do is boil a jug full of water, walk away, forget to make your cup of tea or coffee, and then come back and boil it again. The amount of energy required to boil that is quite a lot. Okay, and the reason for that, okay, have a think about it. What do we know about water? Okay, the reason for this is, of course, that water has very strong hydrogen bonds between its molecules, and they're what we need to disrupt to make the water boil when we go from liquid water into a gas. Remembering that this was an endothermic process because we needed to put energy into the system to make this happen. And we have many hydrogen bonds between water, so we need to break all of these in order to be able to cause this phase change. Okay, so the ability for a mass of substance, so say 1 kilogram of water or 1 decimeter cubed of water, to absorb that heat is called specific heat capacity. Okay, so this value gives us an idea of how hard it is to make something increase in temperature, because an increase in temperature is an increase in kinetic energy and tells us a lot about it. So the specific heat capacity of water is greater than most other substances. Okay, so we can cook in oil because oil will get to a higher temperature for the same amount of energy than what water will. Okay, so the strength of the intermolecular forces between a substance gives us an indication of what its heat capacity will be. How easily does it transfer that heat? You've seen this in summer, okay, where you've gone to the beach and you will have really hot sand on a hot day up to the beach, and you've got to run across the sand. And then when you get into the water, it feels much cooler. That sand and that water have both had the same amount of energy from the sun. Okay, if they're both sitting out in full sun, then the water has had the same amount of energy hitting on it as what the sand does. Okay, but the sand will be much higher in temperature than what the water is. The sand will probably be 50 degrees or more, and the water is going to be a nice pleasant 20, 21. Okay, so, and this is because of heat capacity. The sand has a lower heat capacity than that of water, so for the same amount of energy, its temperature will go up a greater amount because it takes less energy to increase its temperature than it does for the water. So when we define this, this is another one where we need to know the units and the exact definitions. Specific heat capacity is given the symbol little c, okay, is the measure of the amount of heat energy needed to increase the temperature of 1 gram of substance by 1 Kelvin, or 1 degree C. Okay, its units are going to be joules per gram per Kelvin, okay, or joules per gram per degree C. It's important to note, okay, that sometimes in physics they will use kilograms instead of grams. So it would become a kilogram of substance by 1 Kelvin, and then this unit would change to kilojoules. In chemistry, we tend to use grams, so we end up with it in joules. Okay, it is important to remember that our unit here is in joules, because when we get to enthalpy, our enthalpy is in kilojoules. Okay, so the specific heat capacity of water is 4.18 joules per gram per Kelvin, and this is actually given in your data booklet. Okay, and this means that it takes 4.18 joules of energy to heat 1 gram of water by 1 degree, okay, or 1 Kelvin. So 4.18 joules, that means if you were heating a liter of water, it's going to take 1,000 times that, so 4,180 joules, to increase it by 1 degree. Okay, so if you're going to go from room temperature at about 20 degrees to boiling at approximately 100 degrees, that's going to be an awful lot of energy that needs to be placed into that system. The higher the value of the specific heat capacity, the more effectively the substance will store energy, i.e. it will absorb that energy with no change in temperature, or it will absorb more energy before a change is seen. Okay, and you may remember this way back in year 7, you did from ice to steam, and you would have taken a mixture of icy water and you would have heated it up, and it goes up in temperature and then it stops for a bit and then it will go up again. These areas here are where the phase change is occurring. So this would be the boiling point of water, okay, at 100 degrees C, okay, and this is while it is changing from a liquid to a solid. Okay, so this is while it is actually boiling. Sorry, this is going to be liquid to gas. The previous one would be liquid to solid to liquid, liquid to gas. Okay, so the temperature increases up until the point where it starts to boil, and then as it starts to boil, we have all the energy being put in until all of it is in the new phase. So this is while the phase is changing. Okay, and you may have noticed that when you boil water, it will, as long as there is water left, stay at a constant temperature, hence why we use it for cooking and things like that. We can get a constant temperature. Okay, so this is all the energy that needs to be put in before the temperature can start rising again, i.e. when it's all turned to a gas. So to calculate the amount of energy required to cause the temperature change of a substance, we use this formula here. This is one that is not given in your data booklet, so you do need to remember it. It is given by the fact that heat energy is equal to the specific heat capacity multiplied by the mass of what is changing temperature. Okay, so that will usually be the solution. Okay, so it is important. The mass of what's changing temperature multiplied by the change in temperature. Okay, so the change in temperature is what we're looking at here. So what this means is for something that has a different heat capacity, okay, then for the same amount of energy, so heating for the same amount of time, so providing the same amount of energy, will cause different increases in temperature. Water has a higher specific heat capacity than ethanediol because of its hydrogen bonding. Okay, so its temperature is seen to increase less than ethanediol, which here it does have hydrogen bonding, okay, but water can form more hydrogen bonds than ethanediol. Okay, so water, remember, can form 4 hydrogen bonds per molecule, so it's a very small molecule compared to ethanediol. We will have more water molecules per amount of liquid than ethanediol as well. So we would have a higher mole of water present, therefore needing more energy to disrupt that. So when we look at this, we need to work out for enthalpy the heat energy change. Okay, so the change in heat energy experienced in a reaction. When we heat something up, there's a change in heat energy. That heat energy is given the symbol Q. Okay, so where we said heat, we use the symbol little q, and it's dependent on how much of a substance there is, the specific heat capacity of the substance, and the change in the temperature that we observed. So the final formula that we get is Q equals mc delta T. You can use E, but Q is what is used by standard. Okay, the heat energy is determined in joules. The mass of the substance is always in grams. The specific heat capacity, we match the units of our specific heat capacity to those of the components that go up to make it, so joules per gram. And the temperature change is in degrees C or Kelvin, remembering that each mark on the Kelvin scale is the same as 1 degree C. So let's have a look at a couple of questions. So if we want to calculate the energy required to increase the temperature of 1 kilogram of water by 10 degrees C, okay, if the same amount of energy is used to heat 1 kilogram of sand, calculate the temperature rise. So first things first, we need to calculate the energy. So we're using Q equals mc delta T, or Q equals mcat. So we want energy, so we're looking for Q is equal to the mass. Remember, this has to be in grams, so it's going to be 1 times 10 to the 3 grams, or 1,000 grams for a kilogram, multiplied by the specific heat capacity of water, which is 4.18, and then multiplied by our temperature change. And we're increasing it by 10 degrees, so it's going to be multiplied by 10. And when we work that out, we get 1,000 multiplied by 4.18 multiplied by 10, and it's going to be 41,800, and remember our unit is joules. Okay, so now we're told the same amount of energy is used to heat 1 kilogram of sand. Okay, calculate the temperature rise of the sand. So we've got Q equals mcat again. Now we're looking for delta T. So going to rearrange. Delta T is going to be equal to mc Q on mc. Okay, so now delta T, remember our Q value is 41,800, and then we're going to divide that by the mass, again is going to be 1,000, or 1 times 10 to the 3, multiplied by the heat capacity of sand, 0.48, which is going to equal 41800 divided by it's going to be 87.08 degrees C. Okay, so where water will increase by 10 degrees, sand would increase by 87 degrees. So we can see that in this case, we're going to have a much greater temperature rise from the sand. This point here, the density of water is equal to 1 gram per centimeter cubed, okay, is important because this is how we go from knowing a volume of water to a mass of water. Okay, so if the question had said 1 decimeter cubed, then that would be the same as 1 kilogram. Okay, 1 decimeter cubed is going to equal 1 kilogram because I have 1,000 centimeters cubed at 1 gram per centimeter cubed. Okay, so 1 gram per centimeter cubed is the density of water that we assume doing these calculations. Okay, so let's have a look at it. There's a couple of quick assumptions that we have to make with this. In that case, we were talking about heating water, but many calculations of heat energy involve aqueous solutions. So they might be a solution of a neutralization reaction of an acid and a base, or a precipitation reaction or a redox reaction. They are going to be aqueous solutions. What we do is we assume that the specific heat capacity, okay, the specific heat capacity of an aqueous solution is equal to that of water. Okay, so when we're doing these calculations, we always use 4.18, okay, but you must remember that this is an assumption that we make. It means that experimentally we may see some differences in values because the specific heat capacity may not be the same as water. Okay, so This is also something that you may think about doing as an IA, actually checking the difference between the specific heat capacity of water and an aqueous solution. Okay, but it is an assumption that we make, that the specific heat capacity of the aqueous solution is the same as that of water. Okay, and clearly the more concentrated the solution, the less likely that is to be true. Okay, so let's have another look at the question here. Pause the video, have a go, and then come back and have a look at the solution. Okay, so hopefully this is what you came up with. We're going to use Q equals MCAT again. We've been told that the beaker contains 100 centimeters cubed of water, which is going to be equal to 100 grams of water. Okay, so this is going to be 100 grams of water heated using a Bunsen burner over 10 minutes. So we know that the density is 1 gram per centimeter cubed, so that gives us 100 grams of solution. Okay, our specific heat capacity is 4.18. The change in temperature is from 15 to 80. So we're going to have 80 minus 15. The total change in temperature is going to be 65 degrees. Substitute those into our equation, and we're going to get 100 multiplied by 4.18 multiplied by 60, which is 27,170 joules, or 27.1 kilojoules in 3 significant figures. Okay. And that is essentially how we go about making finding out the amount of energy that has been put into a system. Okay, so if you think about this, we could now say we know that this reaction put out 27.1 kilojoules of energy. Okay, so we know it was an exothermic reaction because the temperature went up, and then we can therefore work out how much energy exactly that reaction gave out. Okay, another question for you to pause and have a go at, and this is the last one before we finish up this video. Again, this time we've been given the amount of energy, so we've been given Q. The mass is a 500 gram sample of copper. Okay, so it's 500 grams because we're not looking at a solution this time. Okay, the specific heat capacity of copper you would have had was given to us in the question. Substitute in and then solve for delta T. So we're going to end up with Q divided by MC. You should have come up with 140 degrees. Okay, and therefore that was the temperature change. So to properly answer the question, we need to add the initial temperature of the block, which means that the final temperature of the block would have been 155 degrees C. So what I want you to think about is how this relates to enthalpy. Okay, we said that enthalpy, or delta H, had the units of kilojoules per mole of substance. Okay, which means that in that case, when we work out enthalpy, we need to know the amount of energy, so we find the heat that was produced by the reaction, and then we're going to divide it by the number of mole of substance that produced that heat. Okay, and we will look at that in some of our next calculations in the next video.